We're holding today really to give investors an opportunity to have a direct dialogue with the management team and also to see our newly opened facilities here in Hampshire. And thirdly, we've just had a positive, upbeat trading update, and we're excited about the progress that the company's made, so we think it's good timing in that respect. Solid-state batteries and EVs have been discussed a lot in the media recently. And I think that's going to be a very large and important market, but there are other slightly smaller, perhaps earlier adopting markets that I think are going to be just as important in terms of the development of Ilika. One example is actually consumer electronics, and let's call them domestic appliances, many of which are going cordless over the next few years.
What you see over here is over there scanning electron microscope with EDAX, which is an elemental analysis.
We have heard a lot about analysts saying that it will be 2025 before EVs have got solid-state batteries in them. But actually, most analysts are talking about the mass market when they talk about that figure. And in fact, Toyota will be using solid-state batteries in vehicles at the Olympics next year. And so there will be lots of smaller segments, perhaps high-end vehicles and specific types of transport which will adopt the technology earlier. And that's great for Ilika because it means we can get our product to market before the mass market really takes off. We're working with some huge organizations like Jaguar Land Rover and Honda and Ricardo and McLaren. And you might ask yourself, why are they doing that? Well, the answer is that we're able to work in a much more agile manner than a large R&D organization in a global OEM. And because of that, we can make progress in this particular field, which is quite demanding and needs a lot of innovation. We can make that progress much more rapidly than we could within the framework of a larger organization. We used our miniature thin film batteries to demonstrate that we understood solid-state batteries and we could get them to work as rapidly as possible and get them into the market. And actually, that market is the one that's generating the most commercial demand for our product at the moment. So we have a number of programs with deployments in medical devices and industrial Internet of Things, typically for powering wireless sensors. Having said that, the Goliath program really addresses an even larger market, and there is a couple of years of development that's needed for that technology before we will see it in products. But it is a nice opportunity for us to address as a continuation of the revenue growth of the company that we're projecting over the next few years.
The area I'm most excited about in terms of the trip that I've made is actually seeing the facilities. It brings to life that there's a good number of scientists working on a number of the challenges that have been tasked for Ilika as part of the Faraday project. In particular, the identification of a manufacturing process that can scale and provide the cost reduction that's required in order to get this off the ground.
The understanding I got regarding the performance of the battery, regarding stability, regarding safety, I think all of these factors are very important in terms of commercializing this technology in the long term.
There's a huge opportunity which could see this becoming the dominant technology in EV batteries at a time when that industry is maybe 10 to 20 times bigger than it is today.
Today has been a great opportunity to engage with the investor community, and we're very excited about the prospects for the company in the coming years, and we look forward to giving further updates on the company's progress in the coming period. Morning everyone, a warm welcome to Ilika's Investor Day. We're going to have a run through with a presentation from myself and then a presentation from Asad, who is a very well-known and respected analyst from Berenberg, and then Adam Collins, who is going to speak about the EV roadmap from Liberum, and then we're going to have our Q&A session after that. So hopefully between the three of us, we're going to cover a lot of the ground relating to solid state, the battery industry, and then the EV roadmap. So hopefully there's a wealth of information that we'll be able to communicate. So for the avoidance of doubt, Ilika is a specialist in solid-state lithium-ion battery development. And the picture that you see there is a wafer of our M50 batteries that we make on our pilot line, which some of you may have seen on an earlier visit. And the picture in the bottom right of that slide is actually a thinned M50 balanced on the edge of a £1 coin. So you see how thin these devices can become. And I'll come back to the application for these M50s later on in the presentation. So Ilika's history, for those of you who might be new to the story, we're about 15 years old, and when we started the company, we specialized in the rapid development of new materials, in particular for energy storage and electronics applications. And we used that rig that you see pictured there for the rapid development of these materials using a systematically varying array, a library of materials that we can deposit in an automated fashion. Toyota came to us about 10 years ago, perhaps one of the more far-sighted of the automotive companies looking to develop solid-state batteries because they were worried actually about the safety profile of the lithium-ion cells that they were putting into their Prius and worried about triggering a recall of their vehicles through to, because of a vehicle fire. So we actually took the jointly held IP that we developed with them, and we came up with a miniature solid-state battery family that we've been commercializing over the past couple of years, the M50 being our most recent launch in the summer. We have now actually decided, due to commercial demand, that actually making large format cells is a good extension of our roadmap. And we have a number of partnerships with the automotive industry that I'm going to come back to later on to support this, together with funding from Innovate UK. We've attracted about £5 million worth of grant funding from the UK government to support that program. So you'll have read about solid state in the press, and you may have thought, what's all the fuss about? It's an innovative new battery technology, and it's got some intrinsic advantages relative to standard lithium-ion technology, which makes it very attractive for some of the applications that we're going to cover today. I've taken the liberty of giving some of the benefits a double tick, and that's really just to sort of emphasize where the real strengths of this technology lie. Temperature range has been an issue with lithium-ion cells for a number of years. And if you actually heat a standard lithium-ion cell above 60 degrees C, it will start to swell. And that's because it's got a liquid organic electrolyte that starts to evaporate when you heat the cell. And if you continue to heat it, you will burst the cell because of the pressure of the vapor that accumulates inside the pouch, and you will trigger a runaway fire, which is actually very difficult to put out because lithium metal burns very intensely with a beautiful bright flame. So if you can avoid that by formulating a solid version of a battery, then actually you can heat and operate those batteries far beyond the current operating temperature. And some of the applications I'll cover later on emphasize that benefit. You can also trickle charge them. They are rapidly charging, so that is of great benefit if you want to charge your vehicle rapidly. And of course, one of the adoption issues with EVs is that people want to be able to drive them like they drive a petrol car. So when they pull up because the battery's flat, they want to be able to recharge that in the same way that you fill a tank full of petrol. And that's actually been a bit of a challenge with batteries up till now. They are more compact, so they're rule of thumb about half of the volume of a standard lithium-ion cell. And also that safety profile, last but not least. So how have we gone about addressing this technology? We've actually done it really by scaling up the magnitude of the cells that we make. We started with that high throughput screening. We identified electrolytes, solid electrolytes, which are all about the transfer of lithium ions from one side of the cell to the other. With Toyota, secured that IP. We then turned that into a product, a miniature thin film, Stereax, solid state cells. And now we've added our pouch cells to that roadmap. And the scale of solid state cells throughout that roadmap has gradually been increasing. So what are the markets that we are looking to address? This maps our product portfolio onto the different addressable markets. The M250 was the first product that we made, the first thin film battery, and that is particularly useful for combining it with an energy harvester and using it for a smart building. So you can make a little wireless thermostat that you can put on the wall, but also you can use this for asset tagging to be able to track high value assets through a building, for instance, in a hospital. The P180 is a ruggedized version of the M250 and is designed for industrial deployment. So typically in areas where there may be a high temperature that you're trying to operate in, say in a power plant or a process plant, or perhaps close to an engine, or maybe where you really need a long life because of the long cycle life of solid state, you can deploy these cells, fit them, and just let them continue to operate. The M50 is really the thing that benefits from miniaturization, and this is particularly useful for deployment in medical devices. If you really need an implant, then you want that implant to be as small as possible. And by using a photolithography process, we're able to make tiny little devices like the one in my opening slide that can power integrated medical devices. So this is an exciting area, a high margin, interesting early adoption market for this technology. And then we've got Goliath, which is our pouch cells. This is probably the market that you read about the most frequently, for EVs, where you're looking for all of those things we were just talking about. So high power, high energy density, high capacity so that you can drive the vehicle as far as possible, and also intrinsically safe. So in terms of the commercial highlights that we've talked about over the last year, the deployments that have been most important for these thin film batteries, we have deployed it in a perpetual beacon for high value asset tagging in a hospital in Scandinavia. We've also put these cells into turbine blades for wind turbines, and this is to monitor the strain of the turbine blades. If you're managing a high value asset, say in the North Sea, and you're trying to maximize the life of that wind farm, you are really keen to make sure that you know when the turbine blades are starting to deteriorate so that you can put the turbine into a condition where it's safe before it fails catastrophically. We've also got a deployment with Network Rail, which is to measure track strain, and this happens when you get extremes of temperature, in particular during the summer, where you can get buckling of rails. And the last thing that Network Rail want to have to do is deploy a maintenance crew to be able to inspect rails. If they can get that information remotely and then decide who they need to send out and do that as infrequently as possible, that keeps their cost base down. We've recently started an environmental sensor program, which is effectively a fit and forget solution that you can put into an urban environment to measure the pollution content in that environment. And then the final one is a medical device deployment, which is in fact a neurostimulator, which is where a current is put into the peripheral nervous system to be able to address various diseases, including diabetes, so it can stimulate the pancreas to release insulin. And these are the partners that we've got. Litricity, which is a spin-out from Sharp Europe. Titan Wind, which is China's leading wind turbine manufacturer and the fourth largest globally. Network Rail, who you know, many of you will have used their services this morning in order to come here. EPs, which is a specialist in the electronic components that allow us to build these beacons, and then a leading biomedical partner. The next question is, that's great. How do you take the technology from its deployments where it is now, scale it up to markets that start to generate significant revenues for the company and its shareholders? So, manufacturing is absolutely key to this. We were able to make solid-state batteries at a fairly early stage in the high-throughput rig that some of you will have seen that we showed in our second slide. But actually, we now have a pilot line that can make just over 10,000 cells a year, which we operate here in Southampton. That is an operating facility which is allowing us to ramp products revenue. The next step in the scale-up is with Semifab, which is a MEMS fab up in Scotland, and that will allow us to increase production by a further order of magnitude. And that is where we actually put larger scale equipment into a facility, and it allows us to generate and produce hundreds of thousands of cells. And then beyond that, the next scale up is to one of the larger fabs, for instance, one of the large Asian fabs, where you might get into a licensing model in the larger volumes. So just a few minutes really to reflect on the business model that we are now deploying. So the pilot line that we have operational at the moment, and this is true actually for the thin film batteries that we're currently manufacturing, and also in due course the new facility that you're going to visit later on this morning, allows us to actually be a battery manufacturer. So we are selling batteries. Now they are rather expensive at the moment, so the small quantity that's available means that we have to charge a significant premium over and above what you might pay for a battery if you went down to your local Tesco's and bought one off the rack there. But it allows us to actually develop and really ruggedize the technology, make sure we understand exactly how you make these cells. It gives us a lot of expertise and know-how in the area. So we actually take POs and contracts for small numbers of cells at the moment. The next stage is really that manufacturing partnership, for instance, with Semifab and others, around manufacturing larger quantities. And actually, we expect at the moment that we will probably continue to receive the PO and the contracts, but we will operate as a fabless manufacturer. So this is very common in the semiconductor industry. They outsource a lot of the production of their product and don't make much themselves. They are the design authority, but that production is taken care of by the supply chain. And that's what we'll do. The Semifab partnership will be manufacturing wafers, but we will actually manage the back-end processing of those wafers, the dicing, the thinning, the stacking, etc., with supply chain partners. And then when you get to significant volume and you go to a large fab, that's where you get into the licensing model that we've talked about previously, because there you've got a fully developed and demonstrated business model that you can roll out into a much larger facility. And that's where you're more likely to be able to enter into a licensing model. Right. That was the overview of where we've got to with thin film. Let's now change gear a little bit, talk about Goliath. This is really all about being able to address some of the substantial market drivers, some of the large market forces that exist around EVs. And this is a slide actually that reflects some of the targets that have been set out by the UK Auto Council. So these are numbers that really just indicate where batteries in general needs to get to, rather than solid state in particular. So first of all, there's some quite aggressive cost targets. One of the barriers to adoption actually for EVs is that relative to an internal combustion driven vehicle, they are still quite expensive, and a large component of the vehicle cost relates to the battery pack. So there's a big appetite to drive down cost to actually lower than $100 per kilowatt hour at pack level over the next 15 years. So that's actually quite an interesting challenge. The next challenge is really around energy density. So people want to double that energy density. They also want more rapidly charging vehicles, hence the power density driver. They want safe vehicles. They want a long first life for the battery packs. They want to be able to operate at higher temperature. And they also want to be able to predict when that failure is going to happen, if it is going to happen. And it has to be possible to recycle the cells. And you'll have heard about the advantages of solid state and what I've just said and thought, this slide sounds quite familiar. But actually, it demonstrates that solid state maps on very nicely to the long-term roadmap for the requirements for EV batteries in general. And recyclability is particularly important, is going to get more important actually, as the number of lithium-ion cells proliferates, because you're going to want to be able to handle those cells at the end of their lives and put those valuable metals and materials back into the supply chain. And if you haven't got that toxic liquid electrolyte, if you've just got a solid state battery, then you can actually process that solid state cell very effectively and reduce it back to the constituent parts that you need in order to make a battery second time round. Use that cobalt, use the lithium again in the supply chain. So this is the sort of magic chart really, because it demonstrates where battery technology needs to get to in order to really start to satisfy some of those capacity and weight goals. And the Goldilocks zone is right on that XY axis. You effectively want to have high gravimetric energy density as well as high volumetric energy density. And what that means in layman's terms is that you need a lightweight, compact battery. And if you're on that XY axis, then that's how you deliver that. And what you see plotted there are all of the reference 18650 technologies. So 18650 is a sort of lithium-ion standard. So those of you who own a Tesla own many thousands of 18650s. These are cylindrical cells. In fact, Elon Musk has come up with a slightly bigger one, a 21700 version, which is effectively just it's like an 18650 on steroids. But you put thousands of these cylindrical cells together in a pack and you use them to power your EV. So you need to come up with something that's better than what they can deliver. And solid state is that red hatch line up there. So it's got the promise of being able to deliver that performance improvement that people are choosing. What I've also plotted here is lithium sulfur, because you might have read about that. That's actually very interesting technology. It is a lightweight technology. It is lighter than lithium ion, and that's why it's quite interesting. But it is more bulky, and it has got a shorter cycle life. So for that reason, you're unlikely to see it in EVs. You're more likely to see it in perhaps some aerospace applications, well, maybe drones in particular, and where people are carrying large quantities of batteries around. So perhaps in the military, where increasingly our soldiers are carrying lots of electronic equipment that needs to be powered. And so lithium sulfur is useful for that application. So if solid state is so good, why don't we all just use it now? That's one of the questions you often hear. Well, actually, there are still some challenges remaining, and that's really what some of the key players in the market are trying to address, and what we're also trying to address with our pilot line that you're going to see shortly. So the challenges really are around interface resistance, and the methods for making these batteries cheaply and rapidly, and also the stability of the batteries over the type of use cycle that you can expect in an EV. And here's a sort of pictorial representation of some of the technical challenges. On the top left, you see the death knell for batteries, really, which is dendrites. It strikes fear into the hearts of any battery scientist, dendrites. So what these are, they're effectively thin threads of lithium that can grow usually from the anode back to the cathode, and they can short the battery. And if you get a dendrite, then your battery life is over, usually ends spectacularly. And so coming up with a dense matrix that is impenetrable to dendrites is a key part of the technical development. You also need to make sure that your cathode won't fall apart, because actually that is the part of the battery that you're cycling. The lithium ions go in and out of the cathode, and you need to make sure that they can do that freely, but that actually your cathode remains intact. So looking at different materials is what that synthesis and discovery thing is all about. Luckily, Ilika did a lot of that in the early days when we were working with Toyota, when we used that high throughput screening rig. So that's one of our competitive advantages. And then cell fabrication is all about how do you put these materials together and get them to form a robust pouch that you can then put into a battery pack and use in your vehicle. And you'll see some of the equipment we use in order to achieve that when you go around on the tour. So we're not the only game in town. There's a few other people interested in solving this particular problem. And this slide really just shows you a bit of the competitive landscape. So it tries to compartmentalize some of the different technologies and show who is focusing on what. So I've immodestly put Ilika at the top of this chart here with Honda and McLaren. And we're really focused on our oxide-based electrolytes. And this is a class of very stable ceramics. Just about all of the ceramics that we know and use in our everyday lives are oxides, even down to the tiles that are on your kitchen wall. So they're very inert. And it's perhaps one of the most technically challenging areas to develop a solid-state electrolyte because of the resistances that you get to lithium-ion transfer that we heard about in the previous slide. But nevertheless, we've got solutions for those problems and the know-how to be able to deploy this technology. So that's a strong barrier to entry, really, that we're setting up. You also hear about sulfide-based electrolytes, and this is actually probably what Toyota is going to be using in the demonstrators next year at the Olympics. These are relatively easy to make in terms of getting them to transfer those lithium ions and operate in a solid-state battery. It's quite a malleable electrolyte. The downside is that actually they are difficult to handle during the manufacturing process, and you can still set fire to them. And unfortunately, they give off rather toxic compounds when you do that. They give off sulfur dioxide, and with incomplete combustion, you also get hydrogen sulfide given off, which will kill you in very small quantities. So probably not ideal for the mass market. There's also some polymer-based electrolytes, and the purists amongst you might say, well, actually, that's not really solid state, and a lot of our scientists would agree. It's sort of semi-solid state. But actually, some of these polymers can aid lithium-ion transfer. And so some of the companies out there, and in particular, if you've ever been to Paris and driven one of the blue cars that you can rent there in a shared vehicle cartel or club, then that uses one of these polymer-based electrolytes. But the problem with that is that you actually need to heat it in order to get it to operate. So the blue cars need to remain plugged in. They need to be heated to 60 degrees C to get them to work. So the next question is, well, that's great, Graeme. So you're going to come up with oxide-based electrolytes. Is that going to be cheap enough for us to be able to roll that technology out into the mass market? And so this plot shows what those costs are going to do. So to begin with, the costs are going to be high, but actually it's not to do with the intrinsic cost of the materials or the process. It's related to the scale at which you can make these solid-state cells. So we need a mega factory, not even a gigafactory, but we need a mega factory scale before we get to sort of price parity. And then as you put more and more of these factories into production and operation, you can actually see that actually the cost will come down. And that's because the manufacturing process for solid state is simpler than it is for standard lithium ion. You take out that liquid handling. You don't actually need quite so long a battery formation process in order to make the batteries ready for deployment. So how are we going to be able to beat the competition? Because there is a bit of a global race going on. Well, we use silicon as an anode material. That's a bit of a differentiator. We've got a lot of experience in using silicon from our days when we developed the miniature Stereax cells. Most of the competition are actually using lithium metal anode-based technology. We've also got a lot of materials innovation behind us, so we've got a portfolio of materials that we can draw down on from that high throughput screening. And also we're pretty agnostic when it comes to the cathode that we use. We can just take best in class, so if a better electrolyte comes along, we can integrate that into our designs. So these are the lessons from Stereax. We've basically come up with a formulation and a technology development roadmap that allows us to address these challenges. And we've also come up with a roadmap for the pouch design that gets us from the alpha cells that we are producing at the moment that you will see in the facility through to much larger pouch cells with a larger capacity that you can put together in order to power an EV. And actually, we're not looking to do this on our own. We currently are working with Ricardo, who've got a lot of expertise in battery management systems. So we're focusing on the cells, but you need to put these together into pouches before you can power a vehicle. And Ricardo are extremely keen to get early access to the technology and make sure they understand how they're going to be able to sell their BMSs going forward. Our roadmap for increasing the energy density of our cells is very well defined. We're not going to come up with a holy grail at day one. So the alpha cells that we will be making this year and into next year will not be the final solution. And we have a series of milestones that we're going to be working through over the next few years. This work is supported by that Innovate UK funding that we've secured that will get us to pretty much the theoretical limit of what can be achieved in terms of energy density using lithium ion as a charge transfer medium. I'm not going to say too much about the pre-pilot line. This was opened in the summer. We built this really rapidly. We moved from a design through to a functioning pilot line in what felt like 6 short months. The reason that these big companies are working with us is that, not only have we got the technical expertise to be able to deploy the technology, but also we can move in an agile manner. And frankly, within the frameworks of these large OEMs, sometimes that's a bit of a challenge. So we've got 3 programs under the Goliath umbrella where we're working together with Honda and Ricardo, McLaren and JLR, looking at slightly different objectives for each of these programs. So Power Drive Line is all about rapid charging. Moses is all about developing a high-performance vehicle. You might imagine McLaren's interested in that. And then Granite is all about the low-cost manufacturing process that we are going to deploy to address the mass market. And we also have a lead partner framework which allows us to engage with companies outside of these Innovate UK programs. And that includes not only automotive, but also some of the other interesting markets. And I'll come back to this a bit later, but actually I expect that the earlier markets that will adopt this technology will include things like consumer electronics and domestic appliances, because there is an opportunity to actually put solid state into the cordless roadmaps of a lot of the companies that are looking to, for instance, make cordless hairdryers, cordless vacuum cleaners, and things like that. And that is a big market opportunity. So in terms of timelines, of course, we all want this yesterday. John Tinson, our VP of Sales, said to me, he said, Graeme, if we had a factory making hundreds of thousands of these right now, it would be like shooting fish in a barrel. And because salespeople generally try and reel in expectations rather than inflate them, I was thinking that was quite interesting. So that there is a big demand for solid state out there. And we are pushing the team as hard as possible in order to deliver that. I think we've hit our earlier milestone of setting up the facility and commencing internal trials. We're starting to produce our first alpha cells, and so we're in that middle bar at the moment, the Ilika production of alpha and beta cells. And so alpha cells are cells that we test internally to generate data, and then beta cells are cells that we give to our partners for them to validate what we've found. And you can see that by mid next year, there will be beta cells available for them to validate. And then, of course, we're going to build some battery packs. So it's all well and good having the cells, but then we start to need to put a few hundred of them together to make a larger pack to demonstrate that at scale. And then we'll be moving to a larger scale after that. And that's where I mentioned the BIC. Now, that makes the scale-up of Goliath relatively straightforward for us. Because, of course, what we don't really want to do is trying to find the capital in order to build a large factory. So the pilot line will give us the initial quantity that we need. The BIC is really in this central bar here. So that's the Battery Industrialisation Centre, which has been already funded to the tune of about £80 million by the UK government. That's being built up in Coventry. And they're very keen to make sure that they have got solid state capability in there, and we're in discussions with them to deploy our technology there. And then, of course, we move into larger scale manufacturing. That's our mega factory, really, and gets us to scale for some of the mass markets. But in terms of adoption and early deployments and commercial revenue to Ilika, that can start flowing right from the pre-pilot line onwards, because we'll be able to make smaller quantities of expensive cells in that facility, and then we'll be able to ramp that revenue up in the BIC, and then, of course, get to the mass market later on. Right, so we've just issued a trading update. Some of you may have seen that yesterday. Commercial revenue up, total revenue 50% up on the same period last year. EBIT loss dropping, that's nice as we push towards profitability. And cash in the bank, Steve has been fantastically assiduous in securing R&D tax credits from HMRC, and that meant that actually post-period end we were able to increase our cash balance. So we're actually at about 2.5 million, something like that now, Steve. And the plan is, as we push towards profitability, revenues increase, loss decreases, cash flows improve. So, of course, I'm not really allowed to show you detailed forecasts of where the company is going to be going, but I wanted to show you the shape of the business and the shape of the revenues going forward. So, we often get a question, what does the commercialization look like in terms of revenue ramp for Stereax relative to Goliath? So for Stereax, we already have pilot production. We've already got commercial revenue from producing those small quantities of thin film batteries. And when we get into the transfer to semi-fab and other medium-sized partners, that will push the company and that particular part of the business through to profitability, because we'll have the scale of the revenues that we need for that. We will max out the capacity at that medium-sized fab, and then we will be able to transfer the technology into that licensing model we were talking about earlier in the large fab. For Goliath, it looks similar but slightly different. At the moment, we've got a lot of grants revenue, and when you have a look at our P&L, you can see that that £5 million of support that we're getting from Innovate UK is going a long way towards covering the cost of operating the facility that you're going to see. But of course, we want to wean ourselves off that grants revenue over the next couple of years and replace that with commercial revenue from producing small quantities of samples at our pre-pilot line. But then I think that the revenue ramp is going to come from some of those early markets, consumer electronics and domestic appliances. And then we will see the advantage of larger scale production in automotive, as that gives us the additional slice on top of that increasing revenue cake. So just to wrap up, in summary, solid-state batteries are going to be a very disrupting technology. They're going to enable the uptake of a lot of cordless and electric devices and components that we're starting to see accelerated uptake of right now, even with standard lithium-ion. Investors have actually been taking positions in the technology, often via SMEs. So we do have quite a lot of demand from a number of different types of investor groups. And I think that we offer a lower risk investment proposition because of our track record in demonstrating solid state in miniature cells, but also our capital light model. You know, we're not trying to raise capital to build a gigafactory here. This is very much a scalable model that we think is addressable with the pools of capital that we can access. And also, you know, the grant support from Innovate UK is doing a lot to leverage the shareholder investments that we're making on an approximate ratio of 2.5 to 1. So, you know, it's a very attractive proposition in terms of investing in the technology and developing it. Thank you. We will welcome Asad to the stage, and he is going to talk about battery technology and its development going forward. Thank you.
Good morning, everyone. My name is Asad Farid, and I work at Berenberg Bank. And for the last 5 years, I've been covering the entire value chain for batteries, whether it's the mining sector, chemicals, automotive OEMs, and what is also happening in recycling, charging infrastructure, and that entire space. Today, I will be talking about battery cost and the role technology is going to play in terms of reducing cost. And before I discuss that, I want to share what the industry thinks right now. Everyone believes that the cost of these lithium-ion battery packs will keep on declining in a linear fashion once we go below $100 per kilowatt hour. This magic number, an electric car will break even with a gasoline car. Everything will be hunky-dory. EV sales will go through the roof. There are two reasons why everyone expects this. They believe that lithium-ion battery manufacturing is like the solar industry. As the scale keeps on going up, your costs will keep on going down. They call this the learning curve. Every doubling of capacity reduces your cost by around 13%. The industry also believes that this industry is like the semiconductor industry. You have a Moore's law here. As the lithium-ion battery technology is improving, your cost is going to go down because we are moving towards high nickel electrodes. And because of this shift from cobalt to nickel, your cost will decline because nickel is cheaper, cobalt is more expensive. I believe that the entire industry is dreaming. There is no Moore's law here, and there's certainly no learning curve. Lithium-ion battery manufacturing is not like the solar industry. It is certainly not like the semiconductor industry. And I will explain why. And I do think that battery costs will be one of the biggest barriers to electrification going forward. But first, let's look at the battery cost in a bit more detail and why the cost has been declining for the last few years. If you look at the top right chart here, this shows you the cost reduction which you've seen over the last 4 years. And as you can see, in 2018, there was nearly a 29% reduction in the cost of lithium-ion cells, 29%, which was much faster than what we have seen previously. And there were 3 reasons why the cost went down. But one of the most important reasons why the cost fell so dramatically last year was that out of the $40 per kilowatt hour reduction in the cost of the lithium-ion cells, $10 per kilowatt hour reduction just came due to the reduction in the prices for lithium, nickel, and cobalt. So metal cost reduction played a very important role here. The other big reason was, which everyone keeps on talking about, is the scale increase which was happening. And yes, it did play a role. The scale increase in 2018, it did reduce your cost. But every year, the fixed cost and the total cost of manufacturing is going down. The benefit of scale is declining every year. If anyone is thinking that the scale increase and the cost reduction will keep on happening, I don't think that concept is valid. And the third very important reason is that the cell makers, whether it's LG Chem, whether it's Panasonic, whether it's Samsung SDI, they're not really making any money. Lithium-ion cells are being sold at a loss, or it is being sold at cost, and that is clearly not sustainable. And I do think that when you look at lithium-ion battery cost, the cost reduction is not going to be sustainable going forward. First of all, I think one of the biggest risks would be the cell makers out there. If you look at lithium-ion cell manufacturing, it is highly capital intensive. You need billions of dollars of funding to set up these gigafactories. Companies like LG Chem, Samsung SDI, and others, they're not stupid. Why would they keep on investing billions of dollars in these gigafactories and then make 0% return on investments, on these gigafactories? You would remember that there was a consortium of companies called Terra E. They wanted to set up a gigafactory in Germany. They needed $3 billion of money. Nobody gave them that investment. That consortium went bankrupt. Northvolt wants to set up a gigafactory in Sweden. Would you give your money to this facility to set it up if you think this is just will be like the solar industry? You wouldn't. That's the main problem here. If I can show you some charts here for lithium-ion cell manufacturing. If you look at the two charts which are given on the right-hand side, you'll see that the amount of consolidation in lithium-ion cell manufacturing is only going to increase with time. Smaller companies are going to go bankrupt, and the big companies are going to gain market share. And as these big projects get delayed, the utilization rates in this industry will only go up. And that is a big risk, because if pricing power goes to these big cell makers, and if they do not pass on the cost reduction which they are achieving by adding more scale, why on earth would your battery cost go down? I don't think it would. And in this chart, which is given on the top right, I've basically tried to assess what your lithium-ion battery cost would be under different ROI assumptions for the cell makers out there. If you assume that the lithium-ion cell makers keep on making 0% return on investments, and you assume that the scale of manufacturing increases from around 18 gigawatt hours right now, the biggest plant out there would not be making more than 18 gigawatt hours. If it increases to around 65 gigawatt hours over the next 5 years, your cost is going to go down from $160 to around $140 per kilowatt hour. But if you assume that the return of investments for the cell makers improve to around 10% over the next 5 years, it wouldn't decline that massively. I think 150 would be where we are going to stop. The other big risk is on the raw material side. When you look at lithium-ion batteries, they're not made of air, they're made of expensive metals, unlike the solar panels which are basically made of silicon. And in this chart, I've basically tried to do sensitivity analysis where I have the cost of the cathode on the x-axis and I have battery cost on the y-axis. And currently, the cost of the cathode is around $24 per kilogram. And in my view, the cathode is a proxy of your metal cost because that is where most of your metals are being used. What this graph shows you is that if your metal prices were to double, for example, it will more or less neutralize most of the scale advantages which you will get by nearly a tripling of your manufacturing scale over the next 5 years. And we have seen nickel prices increasing by 70% year to date. I also do think that cobalt is going to be a big risk. And I will discuss that in a bit more detail later. And the third very important factor which I would like to point out is that when people talk about that there's a Moore's law here, and when you're going to move towards high nickel-based batteries, the cost is going to go down, I think, again, the market is streaming. As you move towards high nickel cathodes, the cost is not going to go down, it is actually going to go up. Why? If I can show you this very interesting chart, which is given on the bottom right over here. This graph gives you the cost split for the different types of cathode materials, NMC cathode materials, by the cost of the metals and the processing cost. And the entire industry believes that as you move towards high nickel cathodes, from NMC 111 to NMC 811, your cost should go down because your metal cost declines. And that is true. Your metal cost does decline slightly. But what everyone is forgetting here is that your processing cost massively goes up. All of these high nickel cathodes are not that stable. And in order to stabilize them, you have to use very expensive surface modification technologies. And if you talk to companies like BASF, if you talk to companies like Johnson Matthey, how are you stabilizing NMC 811? How are you stabilizing ELNO? They are using very expensive surface modification technologies. And the other big problem is if you're using NMC 532 or any high nickel cathodes above that, you have to use a liquid dynamic cooling system. You have to use a very expensive battery management system. 1/3 of the cost of the battery pack is the cost for the battery management system and the cooling system. So if an automotive OEM in China starts using NMC 62 or NMC 811 in a mass market electric car, the cost overall is going to go up. It's not going to go down, which is very important. And that is the reason why if any automotive OEM, if you talk to Tesla, Volkswagen and others, if they tell you that we are going to move completely towards high cobalt, high nickel based chemistries and you're going to remove cobalt from these batteries, again, I think they are dreaming. Cobalt will not be replaced because if it is, cost is going to go up. It's not going to go down. And in my view, there are 5 risks in total to consider. First of all, cobalt, as I mentioned, it is going to be a big risk. Why? Because we have seen cobalt prices declining massively over the last 12 months, which is great. It has helped reduce the cost of the batteries. But in my view, cobalt is a huge risk and pricing most likely will increase going forward. Why? Because when you look at the supply side and when you look at this chart on the bottom right here, this graph shows you that over the next 2019 to 2025, the industry believes that the cobalt supply is going to increase by around 70,000 tons. And as you would have heard, that some of these projects are being cancelled or the production is being lowered. For example, the Kitanga project by Glencore has reduced the production targets because of uranium impurities. Again, you can see that 25% of future production is coming from the nickel projects out there. These are HPAL nickel projects in Asia. These are difficult projects to execute. And if any of these projects move towards the right, the 70,000 tons of incremental production, that is not going to come about. And if you look at the top right chart here, this chart gives you my demand projections for cobalt over the next 5 to 10 years. And I'm being extremely conservative here. Why am I conservative? Because if you look at 2018 and if you look at this bar, you can see that 40% of cobalt demand goes into electronics. And I'm expecting a complete demand destruction over the next 5 to 10 years. Despite the demand destruction, I'm expecting cobalt demand to increase by around 90,000 tons. Why? Because one, for electric vehicles, for mass market electric cars, I do think that NMC 62 and NMC 532 will keep on getting used. The other big thing which the investors are missing is when you look at the commercial vehicles like vans, trucks, forklifts, all of these applications, they will not be using high nickel chemistries. They will be using cobalt-rich chemistries, because if a truck or a van starts using NMC 62 or NMC 811 in a battery, after 3 or 4 years, the battery is going to die. These commercial vehicles are being used on a 24/7 basis. These are not like your passenger car parked in your garage most of your time. So cobalt is a big risk. If cobalt prices go up, I do think that you need to be worried. I will skip some of these charts. I do think that nickel prices have increased and they will remain where they are. And you can ask me later on. And lithium prices, they've basically bottomed out as well. So lithium is not going to help you over the next few years in terms of reducing battery cost. But one thing which everyone talks about here is that we are going to move towards high voltage based chemistries, because if you talk to Tesla, they're working on fluorinated electrolytes, which will help them to work at 5 volts rather than 4 volts in a lithium ion battery pack. And if you're able to increase the voltage, cell voltage from 4 volts to 5 volts, your energy density increases by around 30%, which is great. But fluorinated solvents are very expensive. This shift towards high voltage based cathodes is not going to reduce the cost for you. These will be used in premium electric vehicles, not in mass market electric cars out there. And this brings me to the same point again. If you want to improve battery technology, your cost goes up, it does not come down. And this is where solid state batteries can help. And I did enjoy Graham's presentation. But there's a big problem here. If you look at solid state batteries, they are going to be horrendously expensive. If you talk to most of the companies out there, all of them are using lithium metal based anodes in a solid state battery. And if you look at the bottom left table here, this graph shows you that the cost of lithium carbonate is now less than $10 per kilogram. But if you're using lithium metal in your solid-state battery for your electric car, you need to have very thin electrodes. The thickness of the electrode needs to come down below 25 micron. And the cost of the lithium metal is going to be around $2,000 per kilogram. If you convert that into dollars per kilowatt hour, just the cost of your lithium metal is going to be around $120 per kilowatt hour. At this price, you can buy the best quality lithium-ion cells from the likes of LG Chem and others. So solid-state batteries could be a solution, but with lithium metal, it will only be used in premium cars or upper mid-tier cars, or it will be used in niche applications. For mass-market cars, it does not make any sense. And that is where Ilika could be interesting. If you can potentially use silicon as the anode material, then you can potentially reduce the cost of solid-state batteries. But the problem here is silicon is not stable, and cycle life is a big issue. So if you want to grill Graeme, you should grill him on the cycle life of these batteries. Can we get the right cycle life for solid-state batteries using silicon? If you can, I think that will be a great solution. Thank you.
Thank you, Asad. So we've now got Adam Collins from Liberum, who is going to talk us through batteries in the context of the EV roadmap.
Okay, good morning. For those of you that don't know me, I'm Adam Collins. I work at Liberum. I'm the specialty chemicals analyst and new energy analyst at Liberum. But in a former life, I followed the auto sector, the international car makers. And at Liberum, in the context of covering the new energy sector, I look at the cathode material companies such as Umicore, BASF, Johnson Matthey, and also directly research Ilika. I'm going to start out by talking about the competition that EV batteries face. This is a car which probably isn't on your long-term wish list. It's the top-selling car in the UK, and it's basically based on technology which has been developed over the course of 100 years and is pretty competitive. It's a car that's got a miles per gallon of 50. It's got a range of 800 kilometers. Fueling time less than 2 minutes, and it's pretty affordable. And that's the sort of car in the mass market that the EV makers longer term have to aspire to. I thought it might be worth just telling you where we started the journey. I'm old enough to remember where the EV sector was 10 years ago, when we had the second coming of electric vehicles. And this car on the left here, the RevoWiz, was the top-selling car, believe it or not, in 2008. Noddy's favourite car. It sold about 1,000 units at the time. If you happened to be around Mayfair 10 years ago, you might have recognised it. It had two distinguishing features. It was exempt from the congestion charge, and you could park for free on Berkeley Square. But you can see it had not the most attractive looks. Top speed was unappealing, around about 45 miles per hour, very small range. And one major problem, which is it was defined as a quadricycle, never passed a safety crash in its life, and was pulled from the market in 2011. The car on the right here, I would say, was the sort of first generation of the serious electric vehicles, the 2011 Nissan Leaf. The problem that it had was in those days batteries were costing around about $20,000. This is actually using a relatively cheap cathode material called lithium manganese oxide. And even then that battery was a third to a half of the overall vehicle cost. Actually at the beginning, roughly one half. And it had a 73-mile theoretical range under US ratings. But that was with most of the electronic systems turned off. And as Graeme was talking earlier, these batteries' performance is to some degree affected by extremes of temperature. And in those days, based on home charging, it took the better part of a night to charge. Here you've got an idea of what I think of the roadmap that the auto industry expects from cars. Graeme gave a roadmap for what the UK is targeting. This, if you like, is a view of what's possible and what's acceptable to car makers. And effectively what I'm saying here is you need an acceptable range, which I think is over 300 miles, but preferably 500, similar to a car today. A cost which is close to a ICE, but not necessarily below it. And then there's obviously other parameters which relate to acceptable safety and long battery life. On the cost issue, on the price of these things, I would argue that you don't need something that is necessarily lower cost than an ICE today, to the extent that I buy into the idea that there are other benefits. So torque advantages, a lower cost of electricity per mile than gasoline per mile, and an argument that maintenance costs over time will be less. And those advantages, allied with a belief that the cost of fuel will probably rise over time with carbon taxes, means we need to get close to the current cost of ICEs today, but not necessarily below it. Just a slide here on the bit of the battery I'm not going to talk about, which is the battery management system, the electronics. I'm going to talk mainly about battery materials, which are around about 60% of the cost of the battery. But as Asad said earlier, there's another 40% which relates to the battery management system, and in addition, the battery pack. And the economics of doing that, to some degree, will be dictated by the scale of plants that are being built. Now, all of you are familiar with the Tesla gigaplant in the US. That's got a 32 gigawatt capacity. And what I've done here is I've showed the plans of battery producers through 2025, the new investments, and circled the projects which are going to be the size of Tesla's gigaplant. So effectively, I think there's a total of 12 factories. 3 of those factories are actually Tesla's. It's just started production from its Shanghai plant, which it took 1 year to produce. And it's now talking about the Tesla Europe plant, which is going to be built in a couple of years' time, which will be based in Berlin. We don't know much about that, but each of those are going to be almost a similar size to the US plant. And there's another 9 like that coming around the world. And that, we think, will drive pack economies and, to some extent, economies of scale in the electronics sector. Fussy chart, a different way of showing what Graeme showed with his bubble chart. But it's essentially what we show here is the 3 areas that we think are going to be key to improving cost and performance in the battery for EVs through 2030. And I'm going to be talking about high nickel cathodes, silicon doped anode, and then the solid electrolyte where Ilika fit in. And basically this roadmap here, which is not inconsistent with what you saw in the numbers that Graeme showed here, it's very roughly a roadmap which envisages the energy density doubling over this time frame. But you'll see here, similar to what Asad is saying, a cost reduction which is not keeping pace with that, a cost reduction of roughly 1/3 for a doubling of energy density. So we're going to talk a little bit about the 3 things I just mentioned, starting with nickel-rich cathodes. So in 2010, car makers, faced by high battery costs, were focusing around 2 cathode materials, lithium manganese oxide and lithium iron phosphate. Both of those are low dollar per kilo materials. They don't include expensive cobalt or nickel, but they were relatively low energy dense, and that's why you got the very low range, sub 100 miles for some of the cars that were coming out in those days. Pretty much since 2012, the industry has adopted cobalt and nickel bearing cathodes, either NMC or NCA. These materials which emit the word lithium are lithium based, in the first stage lithium carbonate based, and they typically have 10% lithium and then a mixture of those other metals, nickel, manganese, cobalt, or instead of manganese, aluminium. And first generation was 333, an equal mixture of those metals. And the transition sees us going to 811 NMC. NCA, which is used by Tesla, is already at the 811 level. It's already 80% nickel. And the other car makers are adopting NCA batteries, which will transition to that level. What is that transition about? It's really about 2 things. It's about replacing high-cost cobalt with nickel at 1/3 of the cost, and it's about replacing low-voltage manganese with higher voltage, nickel. And the transition is effectively driving two things: an improvement of energy density at the cell level, which we think is around about 20%, and an improvement in cost depending on the cost of nickel and cobalt metals, which we think is going to be in the region of 10 to 20%. So overall, combine those two, and you have an improvement in the overall cost per kilowatt hour that could be in the range of 30 to 40%. Now that's easier said than done, and Asad sort of touched on this. Here you've got a slide which talks about the bumpy road to high nickel. There's a couple of important offsets or trade-offs that are occurring. First of all, cobalt is helpful for stability, and if you take it out of the battery, the cycle life is degraded. And you can see that in the chart here, which shows Umicore's calculations of what the cycle life for different types of cathode chemistries were, admittedly, just over a year ago. And what that's showing is that the number of cycles you could get out of 811 at that stage was somewhere in the region of 1/5 it was for current generation materials. And that's obviously a sort of significant consideration. The other trade-offs relate actually to cost, and there's a couple of those as I see it. First of all, that you need a different form of lithium as you go to nickel-rich recipes, and those materials today, which are lithium hydroxide, are more expensive. And then secondly, much more effective, much costlier battery management systems. And therefore, whilst there might be a cost per kilo advantage as you switch from cobalt to nickel, there could be some increased balance of system costs. So let's talk about some of the other things that are going on. So the anode has been the poor relation in terms of the two electrodes in the last few years. Actually, it's got more capacity, and therefore most of the research work, commercial development has gone into improving the performance of the cathode. But as the cathode becomes higher performance, so attention will turn to improving it. And we can kind of see a forerunner of this in the batteries which Tesla are using today, because by being high nickel already, they are adopting already lithium hydroxide and some form of silicon-doped anodes. A problem with silicon, which has been touched on, is that it expands during cycling, sometimes as much as 3 times. And therefore, it's very complex to make something that can live for long enough. And the general thinking in the industry is that you might only be able to use it for between 2 and 10% of the composition of the anode. Even at 2 to 10%, that's a big deal, because having 10 times the capacity of the incumbent material, even at 10%, that would double the capacity of the anode and make quite a significant difference. And there are real-world examples here. I mentioned Tesla, but in the portable electronics space, in Japan, Toshiba, Hitachi are producing cylindrical cells for consumer applications, which are using silicon-doped anodes today. Graeme mentioned that he's got the solution to the problem in EV batteries. It'd be interesting to understand a little bit more in terms of how the cycling issues in relation to this are being managed. But it's considered to be quite a promising area in automotive in the next 5 years, albeit at relatively low compositions in the formulation of roughly 2 to 5% and maybe higher in time. Just a quick word on lithium anodes. That's the other way to go. We talked about that earlier. Graeme talked about the fact that lithium is highly reactive. He also mentioned dendrites. The death of the electrode, and there is a perception that in the use of lithium anodes, we generate lifetime compromising dendrites, which may be an issue. If that can be resolved, that's another way to go, to the extent that they also offer similar capacity to silicon. And then I won't dwell on this. My sort of take on solid-state batteries is, yes, they offer quite promising advantages. The advantages are that you're effectively taking out a bulky separator and also some of the intracell materials in having something which is solid, which helps energy density. You've obviously got something that's safer too, and something which I think is going to be increasingly important. They can be configured to be helpful for battery recharging. There are arguments that it will enhance battery recharging speeds if configured appropriately. I like to sort of talk about three potential pitfalls. One is on the manufacturing side, where you've got a semiconductor manufacturing process today for microbattery SSB, and we'll need to move towards a much lower cost mass market approach to manufacturing. The second one, which wasn't really touched on earlier, but I think still is a live issue, is the question of material selection for the solid. Basically, the ion transfer in solid-state batteries is akin to you swimming through treacle. You've got a solid material which is much harder for ions to move through, and therefore we need something that's very thin but also electrically conductive. In addition to that, there are issues with putting electrodes close to a solid material. They can touch, and that creates interface problems which might compromise the electrode life. And then the third area which was touched on was some of the issues around reactivity. But certainly on paper, very, very promising, both in terms of battery charging speeds and the amount of energy that you can get out of a lithium battery today. And just finally, we also touched on this, a couple of things that have proved exciting, but I would argue mainly in the laboratory. So first of all, lithium sulfur. Yes, it's interesting because like solid-state batteries, you can direct a bullet through it without an explosion. Go to Google and you'll see pictures, videos of both solid-state batteries and lithium sulfur that pass the bullet test. Hence, it's interesting in military applications. It offers quite a lot of gravimetric energy density. It's relatively high energy per unit of weight, which of course would be interesting in an aeroplane. But it's a bulky material which we think will not pass muster in terms of the limited real estate that we require for the powertrain in the car. And then finally, lithium air. Interesting to the extent that it's using an electrode which is made from air, from oxygen, potentially very energy dense. But as the slide here shows, no tangible progress in developing cycling capability despite extensive academic research. Quite a big effort has gone into this at Cambridge University. I doubt the cycle life is more than around about 10 cycles today. It's a very unstable material, which we think is a long way from being commercialized. Okay, that's all from me.
Thank you, Adam. That's great. So now we have got about 20 minutes for Q&A.
Could you just talk about the relationship, please, between Ricardo, McLaren, and you? How many people are working at each place? Obviously, McLaren all their engines are made by Ricardo. Just that relationship between the three and how that works.
Yes, that's a good question. So we have got three separate collaborations under the Goliath umbrella. And they are governed by three separate contracts, actually. So the first one is one that we refer to as Power Drive Line. And this is a collaboration that Ilika has got the lead commercial role in. And actually, the two commercial partners in there are Ricardo and Honda. And so the way it's split is that Honda actually give us guidance in terms of the performance and deployment specification for the modules that we'll be building. Ricardo is developing the electrical management or the battery management system, which is effectively how you manage the charge and discharge of the cells that Ilika is making. So that's how that works. And we have a couple of academic partners in that grouping as well, notably UCL in London, that's got some expertise around the preparation of the solids, the materials that we use in order to make our cells. The second collaboration is one that's called Moses, and that's one that's being led by McLaren Automotive. And actually, we are one of the partners together with a US headquartered but Chinese owned battery manufacturer called A123 Systems. which also is developing advanced battery technology, has actually also got some solid state ideas. We are developing a solution for high performance vehicles within that consortium there. So actually, interestingly, Ricardo isn't part of that second project. So in that example, in fact, McLaren are developing the battery management system. And then the third and most recent one that we announced just a couple of months ago is one that's being led by Jaguar Land Rover, and that's the one we call Granite. And that's really all about demonstrating that solid state can be made at a price point that makes sense for the mass market. So there's a lot of process engineering going into that, an analysis of the cost of taking the materials, making the cells, forming the cells, and then deploying them in packs. So, really using actually the expertise that JLR has got in optimizing the cost of the supply chain.
In September, I met A123, and they were saying that they are changing one of their traditional cell manufacturing facilities in the US to make solid-state batteries already. Right. So are you guys involved in that venture, or is that something which they're working with Solid Power?
So A123 is interesting because they have made small investments in a number of different solid-state battery players. So they've invested in Ionic Materials, which is the organization that uses a polymer actually in order to form what I'd call a semi-solid state battery. And they've also invested in Solid Power, which is a company that uses a sulfur-containing electrolyte together with a lithium metal anode. And of course, Solid Power are building a facility to make their type of solid-state battery. I imagine that perhaps the facility that they were referring to is either that one, or it is a one that they are building to use the Ionic Materials polymer.
So there's quite a concern about the energy density of batteries for heavy-duty mobility, and a growing interest in hydrogen because of that. But of course, you have a high energy dense technology. To what extent has there been any discussion in terms of the Faraday project and your other partners in the UK about developing something for the heavy-duty side? And would there be any significant differences in terms of the setup of the battery, based on the particular cycling or durability requirements in that sector? And then just a sort of slightly different one. You said earlier something that was pretty interesting. You said that basically if a company could build a large-scale solid-state battery plant today, there would be considerable interest, or words to that effect.
Yeah.
Why do you think that's the case? Because the perception is there are still a few technological and commercial milestones to get over before that's ready.
Yeah. Okay. So two questions there. First of all, on heavy-duty deployment of solid state. Now, can I just clarify, under heavy duty, do you mean things like earth movers or more like trucks?
Yeah, well, I was thinking actually Class 8 trucks,
Yeah.
Trains.
That's right.
Something that has a long daily range requirement and is very heavy.
Yeah.
But I mean, stationary applications maybe also apply. Interesting to know your thoughts on either.
Yeah. Well, I think, for trucks, some of the benefits that solid state confer on passenger vehicles are also very applicable to heavy goods vehicles. So the fact that you can make lightweight, compact batteries plays into that market equally well. Sometimes the duty cycle is quite aggressive in those environments, and actually, the charge and discharge rates that are needed can be quite high. And I think that actually a hybrid system where you combine any sort of battery technology, not only solid state, with hydrogen fuel cell technology is actually quite a robust solution, particularly where you've got a long-range requirement, where you're looking to travel literally hundreds of miles a day, which of course is radically different to the type of mileage that you might expect for a passenger vehicle, which might only do 30 or 40 miles a day on average. Does that answer your first question?
Yeah, interest levels, has it really registered, or is it a bit too early?
I think there is, the reason I clarified your question actually is that I think it's true to say we're seeing more interest for some of the applications where you might have excavation, earth moving, those types of, let's call them heavy duty machines that do not actually move very fast as vehicles, but use a lot of power as part of their normal work operations. So because they've got a mechanical arm or something like that they need to power. And actually solid state's got some advantages there. So on you had another question, he had a second question relating to
technology readiness.
Technology readiness. So I think the reality is that solid state is not as mature a technology as normal lithium-ion cells. And my point about if you could build a factory, then you would be able to make a very attractive business out of that, is really a reflection on the technology development journey that we need to go to in order to make it sensible to invest in that factory. So I would argue that some of the larger facilities that are being built at the moment for solid state, using different technologies to Ilika's, run the risk of trying to get an early stage technology to market before it's fully proven and ready to be adopted in what are pretty demanding operating environments.
If I could ask two linked questions. The first is around Goliath and the early application. I think one of the points that was made is that perhaps, given potential costs, the first usage will be in that high performance vehicle area. Can you talk a little bit about where you see that early application? And then I guess as a second kind of follow-up, some of the markets that you brought up in the presentation, it seems like there could be a danger that you're supplying prototype markets with prototypes yourself. Is that something that you worry about as well? Right.
Okay, so let's deal with the early adopter market for Goliath first. So I think that it's largely a question of economics and the tolerance of the buyer for a price point in return for enhanced performance. So, if you're spending $500,000 for a luxury vehicle, you're not really worried if the battery pack within that costs $50,000 or $10,000. Now, in the example that Adam gave with the Ford Focus equivalent, that difference becomes absolutely critical. You cannot put a $50,000 pack into a Ford Focus equivalent and expect anybody to buy it. So the reason that the supercar market is attractive actually for electric vehicles in general, but will be important for solid state, is that that there is that tolerance for a higher price point in return for some of the benefits that we were talking about. So in general, I don't think there's much of a product risk for that particular market, because actually those vehicles generally rely on some very well-defined technology that the battery packs are integrated with, so there's not an additional technology risk laid on top. But I think the question is fair for medical devices, for instance, which is one of the other markets that we talked about, where there's this mega trend of moving from passive medical devices into smart devices that have got lots of additional functionality. But one of the reasons why the commercial rollout of medical devices is a bit of a slow burn is that, of course, they have to go through that FDA approval process, which is very robust and means that the devices have to be put through a lot of testing before they're rolled out to the market for general consumption. I'd say also that some of the industrial IoT markets that we're addressing perhaps carry a more attractive profile because you're putting together devices which are cheaper or more generally robust and accessible. You can order the components through established supply chains, and actually the deployment of these things can be quite rapid, rather than medical devices where you're looking at probably 3 to 5 years to get that approval.
Could I just ask a question about business model 1 and business model 2, moving between one another on significant volumes? Could you define significant? And does it vary by market to market? And also, are there other factors you take into account?
Yes, that's a good question. So just to recap, by business model 1, you mean where Ilika receives the contract or the PO from the customer, and we supply batteries to the customer, albeit on a fabless basis. And business model 2 is more of the straightforward IP licensing model. So, in terms of the scale at which that happens, I think it's really driven by the scale of the manufacturing partner. So, when we talk to medium-sized fabs, they're typically turning over in the order of 100 million down to, say, 10 million pounds. So they're in that bracket. And, we will be a component of their total portfolio offering. So, maybe we account for 10% of the business in that fab. And so at that level, you will find that actually our customers, want us to really take the order, organize the supply chain, and provide the number of batteries that they're interested in. And then when you get beyond that, and you get into the 100 million pound plus type of turnover facility, then that's more likely to be a mass market, robust product that's probably been demonstrated in some earlier markets where a license makes more sense and an arm's length type relationship makes more sense.
Thank you. Excuse me, again, 2 questions. Can you talk about the recyclability of the product today? Where is it? What are the problems? And secondly, can you talk about design-in? So where are you in terms of expectations of a timeline for being designed into a consumer product of reasonable volume, let's say? And secondly, an auto, a car.
Right, okay, good. So recyclability. So this is a really interesting one. One of the challenges with recycling normal lithium-ion cells is the fact that you sort of have to pull it apart and drain off this toxic, flammable liquid electrolyte. Once you've done that, you then take the electrode components and you can put them through a grinder and you can start to separate out the metals for further processing in much the same way that you would process ores that are mined, from a large mining facility. I think it's fair to say that, globally, actually, the lithium-ion battery recycling industry is still in its infancy. Perhaps you have a different view, Asad, but, that would be my
It's developing.
Yeah, it's developing. But the promise for, solid-state lithium-ion is that it becomes a simpler process because effectively, and in particular, if you use the type of design that Ilika has come up with, all of the materials in there are like oxides, they're ceramics, which are sort of similar to the stuff you dig out the ground at the mine. So you can basically break up the battery straight away into a set of different powders that you can separate using the normal sort of flotation and flocculation processes that they use for ore processing. So, the cost point for recycling is going to come down with solid state. So your second question related to design-in. and where we are with getting the product rolled out into consumer mass market products and then ultimately automotive. So that's a really important part of our commercialization efforts, and the reason why I flag these different projects that we're working on is that they are early stage design-in activities where you talk to the marketing department of the OEMs. They've usually got this bright idea about which market they want to address, but they're not quite sure how big it is and not quite sure of the volumes. You design your product into their prototypes, and then they go through not only a technical testing program, but also actually a consumer marketing program. And sometimes that's just as complex and the duration is just as long as actually the technical development itself. And then it gets designed in for manufacturing and mass market rollout. So I think for the thin film Stereax products, we have a well-defined portfolio of products where we're going through that field trial and consumer marketing stage. So you can expect probably another year or two of development before that's ready for mass market launch. But volumes are even picking up through that period because we're seeing demand on our pilot line. I mean, our pilot line here in Southampton is going to be maxed out early next year. So we'll be running at capacity in terms of paid for production off that line. And then we'll need to flip into larger scale partnership manufacturing at Semifab or another as quick as possible. And then with Goliath, that's a longer timeline that we're talking about there. But the reason that I flagged earlier revenues from consumer electronics is that we are in discussion with consumer electronics companies to design in Goliath to new products that are due for launch over the next few years. So we were at the first stage of prototype deployment, which will then ramp up in accordance with our beta cell development that you saw on the roadmap for later next year and beyond. And then automotive, well, there will be similar sort of luxury vehicle deployments in the next couple of years. And then that will ramp up as the price point really, which is one of the main drivers, starts to come down.
Thank you. Would you expect to see a product on the market in the consumer space in 2022? Is that too soon?
I think 2023 is the earliest that I've seen for that.
I want, your Stereax cells, they are quite good. The cycle life is appropriate. If you put these Stereax cells on top of one another, can you create a coin cell which can be used in headphones or whatever? Because the reason why I ask is there's so much excitement about these smaller cells, the coin cells. And you have a product which works. On the Goliath side, if I'm not mistaken, you still have some cycle life issues which you need to resolve. But for the Stereax cells, given it's ready, looking at opportunities in terms of commercializing it in slightly bigger format.
Yeah, so the key to getting rapid commercial adoption of Stereax is to find a good fit between what the performance of the cells is and what the application requires. Now, we too have looked at earbuds, and that seems to be an interesting market and one that has grown very rapidly over the last year or so. Typically, the specifications for those devices requires bigger capacities than the Stereax cells are designed to deliver. So remember that a Stereax thin film battery, an M250 has got 250 microamp hours of capacity. And what you're seeing for those earbuds is a requirement for 50 milliamp hours. So there's quite a difference in the capacity. So while that is a very attractive market, I suspect it's more suitable for a mini Goliath than it is for a maxi thin film battery.
Got it. And if I can ask another question as well, like on the silicon side, like that's the challenge here. And for Stereax, like and please correct me if I'm wrong, you have significant cycle life, so that's not really an issue.
That's right.
First of all, for us to understand, like using amorphous silicon, how have you been able to resolve this issue? Like if silicon is not crystalline, if it is amorphous, why would the expansion and contraction issues go away? Or are you coating the amorphous silicon with something in order to stabilize the material?
Yeah, so that, of course, that was part of our secret sauce. But in general terms, the problem with crystalline silicon is that the atomic structure is very compact. So if you try and intercalate a lithium ion into that structure, and of course turn it into a lithium metal atom at the anode, then you cause quite a lot of expansion. And that's what shatters that crystalline material, even though the crystalline silicon will absorb that lithium ion. If you move to an amorphous type of silicon, and that's actually, by the way, what you're doing with doping the silicon, is that you are disrupting that crystalline structure. You create a much more open structure that has got more space to accommodate that lithium ion that's going into it. And therefore, the overall volumetric expansion is reduced. So, for instance, if you look at Shin-Etsu, right, which is a doped silicon material, that's effectively what they've done in bulk with that material, and that is probably the most broadly used doped silicon out in the conventional market. So we use a similar sort of approach with not only making our Stereax thin film cells, because actually you can do that doping using our vacuum deposition process quite effectively, but also in terms of our choice of materials for Goliath. We make sure we choose materials that can accommodate that influx and efflux of lithium without the volumetric expansion, which destroys the cell.
Interesting. And for the Goliath cell, where have you reached in terms of cycle life? Are we getting closer to 1,000 cycles, charge and discharge cycles, or we are quite far away from there?
We're not at that point yet. So with the Goliath cells, we are still developing the alpha cells. And you saw on our timeline that, in fact, that the first beta cells will be shared with partners mid next year. And that's really what that Innovate UK funding is designed for, to support that technical odyssey. So many thanks for your engagement this morning. That was a really good discussion. I hope you enjoy the tour. Thank you.